So let's start. Welcome to one of the last sessions of FOCS. So the first speaker is Noam, this is joint work with Yossi. They're both from Tel Aviv University, and Noam is going to tell us about tree embeddings and beyond. So go for it, Noam. So I guess everybody knows this by now. We'll have 10 minutes of talk and 5 minutes of Q&A for each paper. So over to you, Noam.
Okay. Okay, so I'm going to talk a bit about network design with deadlines or delay, and this is indeed joint work with Yossi Alzal. So I'm going to introduce 4 types of network design problems, and then we're going to discuss the relationship between these problems. So the first type of problem is classic network design in the offline setting. In such problems, you are given as input some graph. You are also given a set of connectivity requests Q. And in order to serve a connectivity request, one has to buy elements from some universe of elements. So elements are some purchasable component. Usually it's something like edges or nodes of the graph. And the more elements you buy, the more satisfied requests you can possibly have. A solution is therefore some subset of elements to buy, which satisfy all requests in Q. And the goal is to minimize the total cost of elements in that solution that you return. So here's a concrete example. So this example is Steiner tree. So here the elements are the edges of the graph, and the connectivity request is of the form connect some node in the graph to the root using bot edges. So you have this root here in orange, and a solution would be this set of edges which connects every request, to the root. Another example is Steiner forest. In this problem, again, the elements are the edges, and the connectivity request is of the form connect some pair of vertices using bot edges. So here each pair is shown by a different color, and here is a solution which connects every pair. The second type of problem is the online variant of the previous problem. So here, this is like the offline problem, except that the requests of Q arrive over a sequence, and at each time the algorithm maintains some set of elements S, which satisfy all previously released requests. So the algorithm maintains this, so every request that is released, the algorithm must buy additional elements to satisfy that request. The algorithm can buy additional elements, but it cannot sell the elements that it has already bought. So here's a request, here are some elements serving it, another request, more elements, and so on, and this is the final solution for this input. The third type of problem, that's network design with deadlines in the offline setting. So this is again like the offline problem seen before, but now each request is also equipped with some time window. So that's release time to deadline. And that request has to be served within that time window. So here you have this timeline adjacent to the graph and the time windows of the requests. A solution is some set of transmissions which occur at various times over this timeline. So here is a solution. It consists of 2 transmissions at 2 points in time. Each transmission has some set of elements. So this set of elements is being transmitted. And the solution is feasible if, for each request, it has within its time window some transmission which serves that request. You can verify that the solution seen here is indeed a feasible solution for this input. And the cost of the solution, which we aim to minimize, is the sum over the transmissions of the cost of the transmission. So the cost of the transmission is simply the cost of the elements transmitted. The fourth type of problem is simply the previous type of problem, so network design with deadlines in the online setting. So here, a request, so here on the left, you can see the offline input. And on the right, you see the input as it is being revealed to the algorithm. and it is being revealed over time. As time advances, more requests are revealed to the algorithm, and at every point in time, the algorithm may choose to either transmit a solution, to transmit some set of elements, or to do nothing. And the request is revealed only upon the beginning of its time window. So here Q1 is revealed to the algorithm, time advances, Q2 is revealed, Q3 is revealed. Now Q1 has reached its deadline, so the algorithm transmits some set of elements serving Q1 and Q3 in this case. Time advances, another request is released, and so on until the input is over. Now, let's explore the relationship between the variants we've seen. So this relationship can be expressed in terms of reductions from one to the other. So the online problems are harder than the corresponding offline problems if we insist that the solution must be polynomial time. This much is pretty clear. And in addition, the offline problem with deadlines is harder than the standard offline problem. And one might conjecture that this arrow also exists, so the online problem with deadlines is harder than the classic online problem. And the question is this the case? So in fact, there is some element of the problem that we need to describe that I haven't gone through yet, and that is, so we are revealed a request upon its release, so the start of its time window. But are we also revealed the end of the time window at that same time? So do we become aware of the end of the time window at the beginning of the time window or only at the end of the time window? If we become aware of the end only when it arrives, this is the non-clairvoyant case, and for this case, this arrow does exist. However, if we're in the second case and we are revealed the end of the time window upon the beginning of the time window, this is the clairvoyant case. And for this, somewhat surprisingly, the answer is no, this arrow does not exist. And moreover, this online problem with deadlines is in fact as easy as the classic offline problem up to an approximation factor of O log n. And this is the result of our paper. So it is worthy of note, there is also a generalization of deadlines, which is delay, in which the deadline of a request is replaced by an increasing delay function, such that the more you delay in serving the request, the more cost you incur. So this prioritizes earlier service of requests, and deadlines are a special case of this delay problem. Okay, so let's see some problems which were previously considered in the deadline delay model. So one of these is multi-level aggregation. So this problem is in fact like Steiner tree on a graph which is a tree, which is surprisingly an interesting problem in the deadline and delay setting, and for which there are algorithms which are polynomial in the depth of the tree competitive. And in fact, Steiner tree on a general metric space can be solved by randomized embedding to a tree and then using these multi-level aggregation algorithms. This yields an algorithm which is O log squared n competitive, where n is the number of vertices. Another problem is facility location with deadlines or delay. In this problem, a transmission consists of opening a facility and connecting some requests. And for this problem, there is also an O log squared n competitive algorithm, which is also based on metric embedding and applies only to the uniform case in which each facility, opening a facility at a node has the same cost regardless of which node that is. So to summarize these results, we have here various network design problems and the existing results for those problems. And these are the ones we obtain in our paper. And these are all polylogarithmic guarantees which are deterministic and run in polynomial time with a single exception here. In fact, our results can be stated as follows. So the first result is the framework for network design with deadlines, which given exponential time yields a log of the number of elements competitive algorithm. But if we replace this exponential time with a polynomial time gamma approximation for the offline problem, then we can encapsulate it and get a gamma log the number of elements competitive algorithm for network design with deadlines in the online setting, of course. And the same we also obtained for the delay case. However, we do demand for the delay case that this gamma approximation is for the offline prize collecting problem, in which a solution may choose not to serve some request, but instead pay a penalty for that request. So yeah, that's, I guess, all the time I have. So thank you, and please ask any questions.
Thank you, Norm. So now it's Q&A time.
What is the key idea? You didn't say anything about the idea.
Yeah, I don't have the time, but the key idea is having requests. The key idea is surprisingly unconnected to the underlying like metric space, and is more connected to how old the request is. So the key idea is if you have a request and you're doing some transmission, and that transmission has some cost, but it did not serve that request, then the request will sort of hold off for an equally expensive service, like at least an equally expensive service. So if you spend like a cost of 32, and that request is alive before and after that service, like that transmission, then like that request will not agree to be served by like a transmission of cost 8 in the future. That's the underlying idea here. I guess if you wanted to motivate this would be like, if a service is expensive, then it's sort of cost effective for the requests that it does serve. Because like, suppose for a Steiner forest, if you're willing to buy a lot of edges, then any additional request that you want to serve, you already like bought perhaps a large segment, like you're pretty close to satisfying it already.
Okay, thank you.
So I had a very basic question. If you go back to your first slide, it was one of your first slides, or maybe when you're saying easy and hard, you said this thing doesn't hold where the online is this bottom arrow. I see. So this classic online. So why can't you set the deadlines to be infinite? In which case this would be a special case of that.
So if you don't know the deadlines upon the release of the request, then indeed what you can do to prove this error, this is like the non-clairvoyant case. If you don't know the deadlines upon the release of the requests, then like what you can do is release a request on each possible conductivity request with deadline infinity, and then sort of or with unspecified deadline, and then you can create like an online instance from saying, oh, the deadline of that request now arrived, the deadline of that request now arrived, right? You can convert like an online instance to an online with deadlines instance in this way.
But why isn't in the classic online? Why don't you know the deadline? Don't you? Like the deadline is
in the online there isn't. Yeah, like the deadline is it's like an immediate thing. But if you think about like the transmissions that can, okay, what's the difference? I guess if you try to describe like an online instance as like a collection of requests with like immediate deadline, then what would happen is, like in contrast to the online setting where the optimal solution just buys something which serves all of the requests, like the optimal solution has to choose some transmission time. And if it chooses this time, then this request is not served. This is in contrast to the online setting where you don't have transmissions, where you buy something and you can use it forever.
I see. Okay, got it. Yeah, we have maybe time for a quick question. Okay, if not, let's thank Norm and go on to the next.
Okay, so I'll stop the share, I guess.
The slides.
Yeah.
So
Yeah.
I can, okay.
You are the next speaker.
Yes.
Yeah.
So
next speaker is Yuhao Zhang from Hong Kong University. And he's going to talk about fully online matching. This is joint work with Z, Huang, Xiao, Hang.
So sorry, I need to re-enter it so I can share the screen. Wait a moment.
Okay.
Okay.
So you're ready now?
Yeah. It's
okay.
Okay, I'm ready now.
Okay, let's start.
No, it's not this talk. Wait. So okay. So I can start now?
Yeah, please start.
Okay. Hello, my name is Yuhao Zhang, and today I want to give you a very short talk about our paper, Fully Online Matching 2, Beating Ranking and Water Filling. And it's a joint work with Zhi Huang, Zhi Haotang, and Xiaowei Wu. Okay, let's first focus on the title. So fully online matching means the model we researched, and ranking and water feeding are two very classical algorithms which have already been proved to have good performance on fully online matching model. Ranking algorithm is actually a randomized integral algorithm, and water feeding algorithm is a deterministic fractional algorithm. So our contributions is that we beat both these two algorithms in both integral version and the fractional version. So first, let us go into the model, fully online matching. It is actually a generalization of online bipartite matching. Its name is fully online means in this model, every vertices arrive online. Different from the classical one. In the classical online bipartite matching problem, we still have one side offline vertices, but this time no. So what happens at the arriving time of a vertex V? We will not only know the vertex, but also know the edges between V and previous vertices. Let's see the example. When the second vertex arrives, we know that it is connected to the first vertex. And then at the third vertex arriving time, we know it is not connected to any previous vertices. And then someone arrives. Then there's another important timestamp called deadline. At the deadline of a vertex B, that means the last time B can be matched. So maybe this time we can match it to the second neighbor, and everything goes on. Someone arrives, someone goes into its deadline and match one pair, arrives, deadline, and match. So at the end, this time we make 3 matched pairs. And actually, if we know everything at the beginning, we can make 4. And 4 is the optimal solution for this case. So in competitive analysis, if we can prove an algorithm can always keep a ratio like 3/4, then we set the competitive ratio of that algorithm is 3/4. Okay, to make the fully online matching model more reasonable, we add one more assumption. That is, we let the neighbors of a vertex B must arrive before this deadline. That is because not only algorithms, but also the optimal solver should not be able to match a vertex with another vertex that has already been left. So there's no reason to have edges between them. Okay, another thing is, as I said before, it's a generalization of online bipartite matching. So just like the result in online bipartite matching, we know simple observation shows that greedy algorithm has already been half competitive. So the main question should be, can we do better than half? Actually, the classic co-algorithm, ranking and water filling can do. In the ranking algorithm, the ranking algorithm, what is the ranking algorithm in fully online matching? We will draw a random rank from 0 to 1 for all vertices at their arriving time, and we will do matching decision lazily. That means we will wait until some vertex reach his deadline, and we will let it to match to the unmatched neighbor with the smallest rank. That is ranking algorithm. And then what is water filling? Water filling algorithm, the idea is similar. The water filling idea is that we will match an online vertex continuously to the least matched offline neighbor. And if we call water level to be the matched portion of a vertex, it's equal to say we will continuously match an online vertex to the offline neighbor with the lowest water level. So in the fully online matching version, we still do a lazy thing. We will wait a vertex reaches deadline and match that vertex following the water filling idea. So the summary is that ranking and water filling can both achieve the optimal ratio 1 minus over E for integral version online bipartite matching and fractional version online bipartite matching. In fully online matching, we already know that ranking can achieve the competitive ratio 0.567 for bipartite graph and 0.521 for general graph, and water filling can achieve 2 minus square root 2 competitive in both versions. And these two analyses are tight for algorithm, but we do not know whether or not this ratio are optimal. So can we do better? In this paper, we answer this question, yes. In the integral version, we design an algorithm called balanced ranking, which beat 0.567 to be 0.569. And for fractional version, we design an algorithm called eager water filling that is 0.592 competitive. Let me see the time. Okay, then I will talk a little about the ideas. Well, eager water filling, the idea is quite simple. Recall that the fully online version water filling algorithm is a lazy algorithm. We will wait a vertex reach its deadline and then do matching decision. But in eager water filling, that means we will match some portion of a vertex just at its arriving time. Then with this simple idea, we can beat water filling. For balanced ranking, a little bit more complicated. We still make the algorithm lazy, but when a vertex U want to choose partner, previously in ranking, it only cares about the neighbor's rank, right? But this time, we extrally let it consider the water level of its neighbors. Here, water level means the matching probability of that neighbor. And actually what we use is the look ahead water level. It is quite interesting. The look ahead water level means the matching probability of a neighbor V after use decision. That is a little bit strange because use decision actually affects that look ahead water level. And we want to let the look ahead water level affect use decision. So how to do this? We design repeated guessing and adjustments progress, and then this thing can be done. I think it's a very interesting part in our algorithm. And I will talk one future direction. We know equal water filling can beat water filling in fractional version, and balanced ranking can beat ranking in integral version. So one direct question is, can we continue to beat balanced ranking by the equal water filling idea? So that's what I want to say, and that's my talk. Thank you.
Okay. Q&A time. So I have a question. Yeah, can you hear me?
Which slides you want?
No, so my question is, it's interesting that you are beating, it's the main takeaway for me was these natural algorithms are not optimal in this fully online setting.
Yes.
Do you think the algorithms you have are optimal?
Actually, I think no, because we just find some properties that has good performance in the worst case of ranking and water filling, and design algorithm by these properties, and I do not think that tight property.
Okay, where do you think is kind of the gap in terms of so you did something. Where do you think will the next kind of improvement come from?
You mean the property comes from? Oh.
Yeah, I'm asking you to speculate, really.
Yeah. I just talk about balanced ranking because in the worst case of the ranking algorithm, we find that we do not give enough bias to those two vertex who has low water level. So we just give some bias for them. That's our basic idea.
Right.
Yeah.
Or let me put it this way: do you have a conjecture on what would what an optimal algorithm would be?
Okay. I have no detailed conjecture because we haven't get some worst case that we believe can't beat.
I see.
Yeah. It's still quite open, I think.
Maybe related to that, are there other problems where this idea is beyond the specific setting? These algorithmic ideas are useful. In addition to competitive ratio, are there some general principles where these ideas can help in other related problems?
Yeah, I think the one thing I want to say is the calculation method of the look ahead water level. Let's see so by this property we can use the look ahead. We can guess the look ahead water level. I think this technique may help to design many other algorithms in different settings, I think. Okay. Is that okay?
Yeah. Okay, so let's thank the speaker again. And so the next speaker is Sohail.
Yes.
From University of Maryland, and he will talk about stochastic weighted matching. His joint work with Masha, also from UMD.
Do you see my slides now?
Yeah, we can see the slides.
Okay. Yes, hi everyone. I'm going to talk about stochastic weighted matchings. This is based on a joint work with Master Action. We're both from University of Maryland. So let me start with the problem definition. We are given an edge-weighted graph G along with some fixed parameter P between 0 and 1. A random subgraph GP of G is then realized, which includes each edge of G independently with probability P. We are unaware of this random subgraph GP, but what we can do is to non-adaptively query a subset of edges Q of G to see which one of these edges are realized. And then the goal is to find an approximate maximum weight matching of GP by querying few edges. Okay, so alternatively, the problem can be defined as follows. We would like to find a sparse subgraph Q of G that in addition to being a sparse achieves a large approximation ratio, where the approximation ratio is basically defined as the expected weight of the maximum weight matching in a realization of Q over the expected weight of the maximum weight matching in the realization of the whole graph G. The problem has many applications, for example, in kidney exchange, online labor markets, online dating, and it can also be seen really as a graph sparsification problem. So pictorially, what the problem basically asks is, we are given this graph G. This is a realization of G, including, say, each edge with properties, in this case, half. And this is a maximum weight matching of the realization GP. We have to sparsify G to a subgraph Q, such that if we look at the realization of QP, realization QP, the maximum weight matching of QP compares well to the, in weight, to the benchmark, which is the red matching. Okay, so let's see some trivial algorithms. So basically, the first algorithm is we can query all the edges. Obviously, we get an optimal approximation ratio of 1, but this algorithm is not efficient because it has to query up to n squared edges. On the other hand, we can query just one maximum weight matching of G. Here, the queried subgraph has maximum degree only 1, which is good, it's a sparse. But on the other hand, it can be shown that the approximation ratio of this algorithm is actually exactly P, which can be made arbitrarily close to 0. So this is not good. But here's a more interesting algorithm. It was first introduced by Blum et al. In 2015. Here we first pick a maximum weight matching of G, remove its edges, pick another maximum weight matching of G, remove its edges, and finally let Q be the union of all these matchings. Okay. Well, so on the one hand, if R, the number of steps of this algorithm, is a constant, then this subgraph is going to be sparse. And on the other hand, it's known that the approximation ratio of this algorithm is somewhere between half and 0.83, even for unweighted graphs. On the other hand, there's this other Monte Carlo algorithm we introduced in 2019, where here we again pick multiple matchings of the graph, but this time we do not remove the edges. Instead, what we do is we take different realizations of the graph. Here the algorithm is randomized. We take different realizations of the graph, and from each one of these realizations, we pick a maximum weight matching, and then let Q be the union of these matchings. Again, if R is a small, this is going to be a sparse subgraph. And there in 2019, we showed that for unweighted graphs, this algorithm obtains a 0.65 approximation. And we later improved the approximation ratio for unweighted graphs to up to 1 minus epsilon in less stock. In this, but for the weighted case, the best known bound is still slightly above a half for this algorithm. So just to quickly overview what is known, in the unweighted case, we have a 1 minus epsilon approximate algorithm, which queries only a constant number of edges per vertex, so long as epsilon and P are constants. For the weighted case, however, prior to our work, the best known approximation ratio was only slightly above half. In this work, we close this gap. We basically show that for the weighted case, the same guarantee can also be achieved. And we get a 1 minus epsilon approximation by querying only a constant number of edges per vertex for constant epsilon and P. And it's known that some dependence on both epsilon and P is necessary in the degree of our subgraph Q in order to obtain any 1 minus epsilon approximation. Okay. So before going through the details of the algorithm and analysis, let me mention a few of the challenges that we face. First, in analyzing the Monte Carlo algorithm, Note that each one of these realizations from which we pick a maximum weight matching may be very different from the actual realization GP on which our algorithm has to be competitive. In particular, if we pick any of these matchings, say maximum weight matching of graph GI, in expectation only p fraction of its edges are going to be realized in GP. So what we'd have to do is to prove that the realized portions of these matchings can augment each other and construct the heavy matching. And this turns out to be tricky for several reasons. The first one is the Ruza-Samrady barrier, which was pointed out first by Asadi et al. In EC16. I won't go through the details of this barrier, but basically what it says is that in order to go beyond two-third approximation, even in unweighted graphs, we have to use the fact that all the edges in the graph are realized independently. In other words, even if just one edge per vertex is realized in a correlated way, then this setting would not admit anything better than two-third approximation. Nonetheless, I just mentioned that for the unweighted case, we know 1 minus epsilon approximate algorithms. In particular, a Stock 20 paper introduced a notion of vertex independent matching lemma, which we use to break this barrier. And here in this paper, we generalize this to weighted graphs. Just to quickly mention what this lemma guarantees. So suppose we are given this graph G, that's again a stochastic, a subgraph GP of G includes each edge with probability P. Now you give me an arbitrary randomized matching algorithm A, possibly with any correlations. What I give you is another matching algorithm for producing a matching M, where this matching algorithm is very close to your algorithm in the sense that each vertex is matched with roughly the same probability. And at the same time, the matching that I report is also going to have approximately the same weight as your algorithm. But in addition, my algorithm also satisfies a useful independence property, which basically says that if we pick any subset of vertices that are pairwise far from each other in the graph, then the events regarding whether or not these vertices are matched in our final matching are independent events. I won't be able to go through the proof of this lemma, but basically, in proving it, we give a distributed local algorithm that operates on a stochastic graph. And I'd like to emphasize that if the graph was deterministic, this could have been done much easier. And one of the key challenges is that we are operating on a stochastic graph. Okay, so the next challenge that we face is existence of low probability high weight edges. Basically, by a simple linearity of expectation, the contribution of each edge to the optimum solution in the weighted case of the problem is simply the probability that that edge appears in this solution. On the other hand, for weighted graphs, this is multiplied by the weight of the edge. So the challenge really is that in unweighted graphs, if an edge has a small probability of appearing in the optimum solution, then also its contribution is small. But in the weighted case, it could be that this probability is small, but the weight is so large that still the contribution of the edge is large. And this is precisely the reason that we were able to obtain an up to 0.65 approximation for weighted graphs in our solo paper, but could only achieve a half approximation for weighted graphs. It's also one of the key reasons for separations in other settings, for example, the online setting between weighted and unweighted matchings. And roughly speaking, the way that we handle this challenge in the stochastic setting is through a greedy algorithm. We use this greedy algorithm and augment the Monte Carlo algorithm, which picks some of these high weight edges, a constant number of these high weight edges incident to each vertex. And the third challenge that I'd like to highlight is lack of a so-called sparsification lemma. This useful lemma for unweighted case basically guarantees that we can assume without loss of generality that the optimum matching, optimum expected matching, has size linear in the number of vertices. But no equivalent of this lemma is known for the weighted case. The reason is we do not really care about the size of the matching, and the weight doesn't really compare well with the number of nodes. Okay, I won't go through the greedy algorithm due to lack of time. But basically, the intuition is that, as I said, we are going to pick some of the high weight edges, a constant number of high weight edges incident to each vertex. Okay, just to also mention a few words about the analysis, we first look at the greedy edges. We look at the realized portion of the greedy edges, run the vertex independent matching algorithm that I described earlier. commit the edges of the matching that we find. And at this point, we have not even looked at the edges picked by the Monte Carlo algorithm. And then use the independence property of this vertex independent matching lemma to argue that the rest of the edges can be used to augment this matching and obtain a 1 minus epsilon approximation. And in conclusion, we proved that the stochastic weighted matching problem admits a 1 minus epsilon approximation by querying only a constant number of edges per vertex, so long as epsilon and p are constants. And one particularly nice open problem is whether or not we can reduce this dependence on epsilon and p to polynomial. We conjecture that this should be the case, but we just don't know how to do it. And it's also interesting to see which other problems admit efficient non-adaptive query subgraphs. In particular, this problem has been studied for various packing problems, minimum spanning trees, and shortest paths. And there are still a lot of other problems to explore. I'd be happy to take any questions.
Let's thank the speaker. Questions? I see a question in the chat. Rupe, do you mind repeating the question?
Oh, yeah. So, yeah, I wonder whether your results are considered about the 0-1 law of the random graph. That is, this for some threshold, if satisfy this the property, and then all the random graphs that have satisfied the property, or none of them satisfied. It kind of strange.
I'm not sure that I quite understood the question.
Oh, yeah. I mean, just for random graph, it has a 0-1 law stuff. It has a weird threshold of the probability. If it satisfies the probability, and then all your graphs satisfy some desired properties, or none of them satisfied, something like this.
Right. So no, I don't think any work has studied this kind of behavior on this setting. But I'd be happy to talk offline to see exactly what you mean. Yeah, I'm not sure how it implies in this, what it indicates in this setting.
I thank you.
Okay, Shazan has a question. Do you want to repeat it, Shazan?
Okay, yeah. So I can look at the chat.
So the question,
yeah,
go ahead, Shazan.
Yeah. So
any possible relaxations for when p is small? So basically, yeah. So we can assume that the p's can be different. So we can assume that the p's are different, and then the realization probabilities of edges are different, and then we have to define p to be basically the minimum realization probability. Then everything should work.
I see.
Next question is by Callum. Is P allowed to depend on N in this problem?
Yes. So in our result, our result is most useful when P is constant. When P and epsilon are constant, then the subgraph that we pick is going to be constant degree. You can let P and epsilon depend on N, but our dependence on epsilon and P is exponential. So the dependency on N should be like really small for the algorithm to be useful.
How much of this is matching dependent versus some other structure, right?
Yeah, so it's highly dependent on properties of matchings, right? So if we use properties of matchings in several different places of the proof, so yeah, so it's highly tailored for matchings. Like, I'm sure that like for very related problems like B matchings, you could do some things, but beyond that, I'm not sure that you'd be able to use the same techniques.
Okay, thank you.
Okay, let's thank Sohail again. And so the next speaker is, I'm not sure who's the speaker for the next paper, optimal anytime regret with 2 experts. Yeah, I can see the screen, but I can't hear you very well, Chris. Hello? You're breaking up. I can hardly make out what you're saying. It's the same problem. Can anyone else hear Chris?
I'll just try to talk louder. Can you hear?
I have a very hard time following what you're saying.
Oh, that's weird. One second.
Your mic looks not good, I think.
Why don't we, should we?
Okay, can you hear me?
Yeah, this is good now.
Okay, good.
Okay.
Let me share my screen again.
Okay, so David, please start. Yeah.
Okay, can you see my screen?
Yes.
Okay, good. So thanks. I'll be talking about our paper on optimal anytime regret with 2 experts. And this is work done by Nick Harvey, myself, Ed Perkins, and Sikander Vandawa. Okay, so we're going to be looking at the classic problem of prediction with expert advice. And in this problem, there's an algorithm A that wants to make predictions given advice by n experts. And in addition, there's an adversary who will set the cost on each of these experts. Okay, so the game proceeds as follows. At each time t, an algorithm chooses a probability vector over the n experts. So for example, 0.5, 0.3, 0.2, and 0. And then the adversary then sets the cost on each of these experts. So for example, you might set cost 1 for the first 2 experts and cost 0 for the last 2 experts. Okay, then the algorithm incurs cost, which is equal to the inner product between the cost vector and the probability vector, which in this case is equal to 0.8. And then the cost vector is then revealed to the algorithm. Okay, the objective is to minimize the quantity known as regret, which is defined to be the cost of the algorithm minus the cost of the single best expert in hindsight. And note that the problem doesn't actually contain any randomness. The algorithm is deterministic, and so the sequence of cost vectors can also be predetermined by the adversary. Okay, so the expert problem has a number of different models. One classical model is a fixed time model, where we assume that the algorithm is provided with a time horizon t in advance, and its goal is to minimize the regret only at that time. Okay, so mathematically, we want to ensure that the regret at time t is at most c times square root t, where we're trying to make the constant c as small as possible. And you could ask whether this model is reasonable. It is really saying that the algorithm will only have a good track record at one point in time. So a more stringent model is the anytime model, where the predictions continue indefinitely. Or in other words, the algorithm's regret must be small at all points in time. More formally, we want to ensure that the regret is bounded by some constant c times square root t, but now the bound has to hold for all points in time. And again, we are trying to minimize the constant c. There's one other model which I will mention briefly, and it interpolates between these 2 models. This is a random stopping time model. And here the stopping time is unknown to the algorithm, but is drawn from a distribution which is known to the algorithm. Okay, in this talk, I'll focus on the anytime model. So let me go over some history of the problem, and I'll state all the known results after they have been normalized by square root t. So in the fixed time setting, Thomas Cover showed that the optimal regret is 1 over square root 2 pi. And this is both the upper bound and the lower bound. So when a number of experts is very large, it is known that the optimal regret is square root 1/2 times ln n. And this is achieved with the famous multiplicative weights update algorithm. Okay, so any lower bound for the fixed time setting carries over to the anytime setting, So in any time setting, we also have the square root 1/2 times ln n lower bound. And in terms of upper bound, multiplicative weights with the correct step sizes can obtain regret square root ln n for any value of n. And this was previously the best result for any value of n. For n equals 2, Lowell and Shapiro also showed a lower bound of square root 1/pi in any time setting. Okay, let me mention that there's also been additional work in a fixed time setting. So for n equals 3, it's known that the optimal regret is square root 8/9pi. And for 4 experts, the optimal regret is square root pi/8. Okay, so our main result is an optimal algorithm in any time setting for 2 experts. And we show that it is equal to gamma/2, where gamma is a constant I'll explain in the next slide. And numerically, the value of this constant is about 0.653. Okay, this is the first type result in the anytime setting. One thing I want to stress is that the important thing here is not really the numeric value of this constant. We really want to understand what are the techniques that might be required to develop optimal algorithms in this setting. Okay, so formally our result is as follows. We show that for n equals 2 experts, there is an algorithm that guarantees against any adversary that the regret is upper bounded by gamma/2 times square root t. Okay, and this bound holds at all points in time. So what exactly is this gamma? So gamma is defined in a somewhat strange way. It's defined as a unique positive root of the function m0 of x squared over 2, where m0 of x is also defined in a somewhat strange way. M0 of x is defined as e to the x minus square root pi x times phi of square root x. Okay, and here phi is the imaginary error function. So at first glance, this m0 function might seem like a really bizarre function, but it is an example of a confluent hypergeometric function. And these functions often appear when looking at PDEs or Brownian motion or random walks. Regret is often closely related to random walks, so it shouldn't be terribly surprising that a confluent hypergeometric function might make an appearance. Okay, perhaps somewhat surprisingly, we are able to get a matching lower bound. We show that for any algorithm and any positive epsilon, we can design an adversary that forces the regret to be at least gamma minus epsilon over 2 times square root t, at least for some time t. And hence we can get arbitrarily close to the upper bound. Okay, so for the rest of the talk, I'll give a little taste of the ideas that go into the design of the algorithm. And if you want more details, you can look at the long version of the talk. Okay, so here's a very high level overview of the approach. We start with the discrete regret problem, and we will obtain via an analogy a continuous regret problem. This continuous viewpoint will allow us to utilize tools from stochastic calculus, and in particular, Ito's formula. And in turn, this will expose the connection between regret and the backwards heat equation, and with this, we will obtain the optimal continuous solution. And once we have the optimal continuous solution, we can come up with an optimal discrete solution using a discretized version of Ito's formula and the backwards heat equation. Okay, so for the last 2 or 3 minutes, let me show you how we can set up the continuous problem and sort of the tools that go into it. One thing I want to mention right off the bat is that for 2 experts, you can specify the algorithm by only specifying how much mass you're playing on the worst expert, because the other expert gets the remaining mass. And so in other words, we can specify the algorithm by specifying a function PTG, where T is the time, G is a gap or the difference in the cost between the 2 experts, and then PTG, the function itself, is how much mass we're placing on the worst expert. Okay, then if you do like an easy calculation, you can show that the regret can be computed by summing up PTG at time t times how much the gap changes at time t. And in fact, you can think of the regret as being a discrete integral of P integrated against the gap process G. And let's remember that we're trying to minimize the regret. One thing I want to note here is that the gap is controlled by the adversary, but for intuition, you should think of the gap as being a random walk. Okay, and so if you want to obtain a continuous problem, one thing you can do is imagine that the gap is evolving continuously instead of discretely, and then you can define the continuous regret as the integral of P integrated against the gap process G. And now again, our goal is to design PTG to make the continuous regret small. And in the discrete setting, we thought of the gap process as being a random walk. In the continuous setting, we'll think of the gap process as being Brownian motion. And now note that the continuous regret is defined as an integral with respect to Brownian motion. And this is an example of a stochastic integral. Okay, so how can we deal with a stochastic integral? To do this, we use a fundamental tool known as Ito's formula, which states that a function r evaluated at some point, some time t and position bt is equal to a stochastic integral of partial g of r integrated against Brownian motion, plus the classical integral of partial t of r plus 1/2 partial gg of r integrated against time. Okay, the idea is to define this partial g of r as our actual algorithm, and in which case the continuous regret appears inside Ito's formula. And so the only remaining thing is to deal with this other integrand. And what we'll do is we'll make sure our algorithm satisfies the magical property that the integrand is exactly 0. And in fact, this identity has a name. It's called the backwards heat equation. Okay, and it turns out that satisfying the backwards heat equation is exactly the right condition. And if you solve this PDE with some appropriate constraints, you will actually obtain the optimal algorithm. And in fact, there's a very clean way of discretizing all these continuous arguments to obtain a discrete algorithm, which is optimal. Okay, so that's all I wanted to say. Thanks for listening.
Thanks, Chris. Time for questions.
I mean, any insights for large N? Any new algorithmic thing that we should take away?
So we have some ideas to deal with 3 experts, but for 4 experts, we're still thinking, like for more than 3 experts, we're still thinking of some ideas. We're trying to extend this idea to more experts. So it's not clear how you would do it right now for like 4 experts or more.
On a similar note, what does a discrete algorithm look like? What is the final algorithm?
Okay, so the final algorithm, you take this potential function that you get, or this function r that you get by solving the algorithm optimally in the continuous case. And then in the continuous setting, we set the algorithm as this partial g of r. The discrete algorithm is to just look at the discrete version of this. So it's a discrete derivative, and that's the algorithm in the discrete case. Right.
So there is no simple interpretation of what algorithm.
There are, you can interpret the algorithm in a way, but that might take a while. I can't explain that in 2 minutes.
Okay.
So I'm happy to answer that question offline if you want.
Okay. Let's see if there are other questions. So we still have 2 minutes. If there are no other questions, maybe you can tell us more about what the discrete algorithm looks like, what this interpretation is. Chris, do you want to give it a shot, trying to interpret what the algorithm looks like in a couple of minutes?
Yeah, I don't have the algorithm. Yeah, I can show you the algorithm.
If you don't have it handy, it's fine. You can take it offline.
Yeah, I can show you offline.
Okay.
But as I said, let me share. Yeah, as I said, there's this function r, and the algorithm is just literally you take the discrete derivative of that, and that's the optimal algorithm.
I had another question. So is it clear, is it easy to see that the algorithm only has to look at the current gap?
No. It turns out that that is the optimal thing to do, but it's not obvious.
Okay. All right. Thanks. Let's thank Chris again. So the next speaker is Yuhao again. This time he's going to talk about Adwords in a panorama.
Okay, hello again, I'm Yuhao, and this talk is about our paper Adwords in a panorama, and it's a joint work with Zhi Huang and Qiankun Zhang. And okay, this time the model is the Adwords problem, and the panorama is the word panorama is a kind of technique, and I will say it later. Let's talk about it later. So okay. The Adwords problem is also a generalization of the online bipartite matching problem. Let us first recall the classical model. In the classical model, we have we are given a bipartite graph, and one side vertices are offline vertices, which is given at the beginning, and the other side is online vertices. These vertices arrive online, and when one online vertex arrives, we will know the edge information between the online vertex and the offline vertices. So what algorithms need to do is to do matching decision at the arriving time of an online vertex, and it needs to keep that each vertex can be matched at most once. Okay, so in the previous talk, the fully online matching it generalized the arriving mode of the classic online bipartite matching. We change all offline vertices to online vertices. And this time, Adwords problem is more like weighted generalization. In Adwords problem, we still have offline vertices and online vertices. And it is used to model the popular AD allocation problem. That means we are now a website, and the offline vertices is the different kinds of ADs we have from different advertisers. And the online vertices may model the user's browsing request. We call it impressions. So what happens? For the offline vertices advertisers, we will have a budget for each vertex. That means the upper bound of money that advertiser want to pay, maybe writing the contract. For example, in this case, the budget is $30, $10, $5, and $15. And then at the arriving time of an online vertex, the impression, we will know the marginal gain if we display some AD to it. For example, in this case, if we display the first AD to this impression, we will have $15 of gain. And if we display this AD, we will have $20 of gain. But notice that because the budget is only $5, so even if we choose this $20 edge, we will only get $5. And this edge is $10. So maybe this time we choose to display the first AD to that user. So we will get $15 in this round. And in second round, there's only one address between the first AD and the second impression, and the weight is 30. But because the budget has already been used $15, it only remains $50. So although the edge is 30, we can only get 15 in this round. So at the end, we get totally $30 gain. But actually, if we know everything at the beginning, we can make 40. Okay, so that's quite similar than all the other online algorithms, online problems. And the previous result is that if we add a small bit assumption, that means we assume the bit is the edge weight is far smaller than the budget, then we have many good results. We achieve the optimal ratio in that setting, and if we assume random rivals, then we can get the 1 minus 1 value compatible ratio by simple greedy algorithm. And in NOID model, we can do near optimal. But if without the small bit assumption, we only know in NOID model it's 1 minus only incompatible. So the most interesting question is that can we beat 0.5 in the general model, the Adwords problem without small bit assumption? So this time in our paper, we answer yes for this question. We find there's a 0.5016 compatible algorithm for Adwords. So let me talk a little about our algorithm. Our algorithm is actually a two-choice greedy algorithm. Two-choice greedy means we will choose two choice, which brings the largest gain and the second largest gain. And if these two gains are quite similar, then we do not only choose the largest one, we will choose two and then random one of them with 50-50%. And then the question is how to make this randomness. One simple solution, maybe do it independently. In different rounds, we just use a fresh random bit to do this 50-50% random. But actually, this independent random method do not help to beat 0.5. So what we do is we apply the online code-related selection technique. That is a very quite new technique, which also published in this year's FOCS, the best paper. They first use it to beat the 0.5 ratio in weighted online bipartite matching with free disposal. And we also use technique. What that means is that we create some negative correlation between different rounds. For example, if an advertiser is chosen in two random rounds, then if it is not chosen in the first round, then it's more likely to be chosen in the second round. That is the negative correlation we created. And the third thing is the panorama view. It is actually another viewpoint to describe the state of an advertiser. Naive speaking, to describe the state of an advertiser, we need to know how much budget it has been used and how much budget it remains. Right? If it's a randomized algorithm, it should look like this. With some property, the budget leaves some blah, blah, blah. With some property, the budget leaves some amount, something like that. But in the panorama view, we view the advertiser as an interval from 0 to BA. BA is its budget. And for each point on that interval, it has a height. And the height is at most 1, means the matching probability of that point. With this view, it makes us possible to apply the OCS technique. Simply speaking, we create negative correlation for each point's different rounds. I can't describe it very clear in this short talk, but it's the simple idea. And then also by this panorama view, it makes it easier to calculate the marginal gain, and so we can know how to do greedy. And the final thing is that how to describe, how to measure two similar choice. As I said before, the intuition is if the first largest choice and the second largest choice is similar, we should use random. But if the first largest choice is far larger than the second one, we should still use deterministic. So how to measure these two things? Actually, we write primal programming and dual programming, and calculates the marginal gain by calculate the dual updating. And then we will choose the choice with largest dual updatings, and everything become okay in this algorithm. Okay, I hope you can understand some of the ideas. Thank you.
Thanks, Yuhao. Questions for you, how?
Actually, maybe let me unmute myself. You have any natural barrier for this approach? Like some number that's clearly not going to be, you can clearly not reach with this approach?
You mean this approach? This approach is, I believe it's not a tight approach. And in Zhi's new research, I think it's not published, they have some upper bound for the OCS technique, but I'm not very sure the number.
Gotcha. Right, thanks.
Okay.
So, yeah, I had one comment which I also sent in the chat. One of your slides. I think so for the small bits, even with random arrivals, random permutation, sorry, you can still get 1 minus epsilon.
So what? You mean this?
The second line. I think you mean random permutation, right?
Yeah, so.
When you say random arrivals, you can get 1 minus epsilon for random permutation also.
I mean the random arrival setting, I think it's 1 minus 1. It's the
so when you say random arrivals, you mean random permutation.
Yeah. Yes, it's okay. It's near optimum also. I'm not sure. Okay.
So for a random permutation, also you can get 1 minus epsilon.
Okay, sorry. It's also in your work. This work?
No, it's a follow-up work.
Okay. I think it's my bad. Okay.
Yeah. So other question, what is upper bound for the general bits?
Upper bound for the general bits, it's still 1 minus over E.
I see.
Okay. But a strange thing is that I see some, in this paper, I see some worst case that shows deterministic algorithm cannot beat 3/4 and randomized algorithm cannot beat 5/6.
I see.
Is that
right?
I'm not very sure. I will do some more.
Yeah. So any more questions for you, how? Okay, so let's thank you, how again. Move to the last talk of the session and the conference. So the last talk is by Daniel Halpern, and it is about resolving the optimal metric distortion conjecture.
Yeah, so let me clear my screen. Okay, can you guys see this?
Yeah.
Okay.
Okay.
Yeah, thanks for the introduction. My name is Daniel. This is joint work with Vasilis Katselis and Nisarg Shah. So this work is generally about voting theory. So I'll start by just giving the overall framework. We're always going to have a set of voters. Here they'll be labeled by the numbers 1, 2, 3, and 4. And these voters have ranked preferences over candidates. And here they'll be labeled by letters A, B, and C. And the voters always tell us their full, complete rankings in this model. We're interested in voting rules. So here they'll always be just functions, deterministic functions for now, that take these preferences as input and then choose a single candidate that wins the election as output. Now, most of the classic literature has mainly focused on what axiomatic guarantees can these voting rules satisfy. So these are things like Pareto optimality or strategy proofness you may be familiar with. Unfortunately, there's lots of impossibility results here, showing that certain combinations of axioms are just incompatible with each other. There's no voting rule that satisfies all of them. So this can make it difficult to compare voting rules and pick which one's the best. So this has led computer scientists to introduce a different way to analyze voting rules. So this was first introduced by Prakash and Rosenshine in 2006, and then this more restricted model was introduced by Ancelovich et al. In 2015. And the main idea is that we assume that these preferences aren't arbitrary, but rather they're induced by some costs. And here we're going to assume these costs actually come from a metric space. And the way to think about this is this metric space somewhat represents a voter ideology. So like the closer a voter is to a candidate in this metric space, the more they align on certain ideas and the more that voter prefers that candidate. Now, the nice thing of the metric space is it gives us a nice way to analyze the quality of candidates. It gives us a numerical way to assess this quality. So our goal here is just going to be to minimize the sum of distances. So the optimal candidate here is the one with the minimum total distance. Now, the reason this might be difficult is the voting rule still only gets the preferences as input. It only gets the rankings. It doesn't know the underlying metric space that induced them. So I'll give you a little bit of motivation from politics for why it might be reasonable to assume that these voters come from a metric space. I hope it shows how general this model really is. So the most basic metric space is just a line. And in politics, is something like the left-wing, right-wing spectrum. And it might be reasonable to assume that voters exist somewhere in this line and prefer candidates that are closer to them, at least in ideology. Now you might complain this is a bit too simplistic. So if you go online, you can find these things sometimes. They're called political compasses. And this is a two-dimensional metric space, and the axes represent different paradigms. And again, voters probably exist somewhere in this space and prefer candidates close to them. You might even complain, this is a bit too simple. Well, this is a very well-studied problem in political science. It goes by a couple names like spatial voting or the Downsian proximity model. At a high level, you can think of it as like a very high dimensional metric space where each dimension is a different issue. And again, voters prefer candidates that are close to them. So it's consistent with our model. Let me give the model a little more formally here. So we're going to have a set of n voters and m candidates. And we'll have a metric over these voters and candidates, so some way to tell their distance. And importantly, as metrics do, it satisfies the triangle inequality. And these distances induce the preferences, or rankings as I was calling them, just in the natural way, where voters prefer closer candidates. If there's a tie, like a voter is equidistant from two candidates, they can rank them arbitrarily. A voting rule here is simply a function. It takes the preference profile's input and outputs a single winning candidate. Recall our goal is to minimize this cost. So the social cost of a candidate is the sum of the distances from voters to that candidate. And the way we analyze voting rules is with this approximation ratio. So in the numerator of this approximation ratio is the social cost of the candidate actually chosen by the rule. And the denominator is the optimal candidate. So it's the minimum social cost over all candidates. And we're going to be looking at the worst case. So this is the worst case approximation ratio over all instances. In this literature, it's usually called the distortion of the rule. And so a natural question then is, what is the lowest possible distortion? So let me show you a bit of what was known prior to this. So this model was first introduced by Ancelovich et al. In 2015. And here in this chart, you can see several well-known voting rules and their associated distortion. So many of the most popular ones have distortion that's like linear or square root in the number of candidates. Even in 2015, when Ancelovich et al. First introduced this model, pretty amazingly, they proved that a certain voting rule, namely Copeland's rule, has constant distortion. So no matter what the metric space is, no matter what the rankings are, the candidate chosen by Copeland's rule will always have cost at most a factor of 5 away from the optimum. And for a long time, this was actually the best that we thought we could do. And it wasn't until a pretty amazing paper last year by Munigal and Wang that they broke this barrier with a brand new rule that achieves distortion about 4.2. So by now, you're probably wondering what a lower bound is. How much more can we improve? So the best known lower bound was also introduced by the first paper by Ancelovich et al. And it's actually really simple. So I think I'll show it here. It'll hopefully showcases the model a little bit. So lower bound goes as follows. We're going to have half the voters that prefer candidate A to B. There's just going to be two candidates here. The other half of the voters say they prefer B to A. Now this is a completely symmetric instance, so there's not really much a voting rule can do. So let's say without loss of generality, it chooses candidate A. Now, what could go wrong? Well, let's say the metric space looks like this. So we're going to have A and B on a line here. Half the voters are right about halfway between the two candidates. They're just ever so slightly closer to A. So these n/2 voters correspond with the n/2 voters here on the left that say they prefer A to B. The other half of the voters over here, and they're right at the exact same location as B. So they have distance 0 from B and distance about 2 from A. And they correspond with voters over here that say they prefer B to A. And if you work out the costs here, you'll see that the cost of A is about 3 times the cost of B. And since this was without loss of generality, see that no voting rule could have distortion strictly less than 3. So then a natural follow-up question then is, can a rule always achieve distortion 3? So the main result of our paper is introducing this new rule. We call it plurality matching. I don't have time to go into the full details of how it works here. You'll have to check out the longer talk for that. At a high level, we look at some bipartite graphs, one for each candidate. And we're going to choose a candidate that has a perfect matching in these graphs. These graphs are matching voters to voters in a way that's matching unhappy voters with that candidate to happier ones. So we're looking for candidates that have more of these edges, and in this case, a perfect matching. The technical part of our paper is proving that no matter what the rankings are, no matter what the election looks like, there's always going to be some candidate that has a perfect matching in this graph. And then we follow this up with the main theorem that proves that our rule, plurality matching, has distortion 3. So it has asymptotically optimal distortion when compared to the lower bound. So just to wrap up, so we have solved the optimal distortion problem for deterministic rules. But there's still lots of room for future work. So our first main connection is we think our techniques are very related to this other open question in social choice theory known as the existence of the core. I don't have time to go into the details here, but there's a pretty big open question, and we think our techniques might have a direct implication here. Next is for randomized rules. So it's known that for all randomized rules, there's a lower bound of 2. It's a very simple modification of that deterministic lower bound. But the best known upper bounds that we have are just 3 minus 2 over m, where m is the number of candidates. And interestingly, the best known randomized rules are no better than deterministic as m grows large. So a really interesting question here is there even a gap? Can randomized rules do strictly better than deterministic rules as the number of candidates grows large? Anyways, that's all I have for today. So thank you for your time.
Thank you, Daniel. Time for some questions. Can you say a bit more about what this bipartite matching is and why there should exist a perfect matching?
Sure. So the bipartite matching is from voters to voters. And there will be edges when, so this will be for a specific candidate A. And for voters on the right, these will be like our unhappy voters. They'll tell us their top choice candidate, who they would have rather had over A. And the voters on the left will match them to them if they prefer A to that top choice. There'll be an edge from a voter on the left to a voter on the right if that voter on the left prefers A to the top choice. So in a sense, it's like if that person on the right comes and complains like, hey, I don't like A, I'd much rather have my top choice, candidate B. If we look at this matching and there's an edge to another voter, we can say like, hey, well, if we switched and chose your top choice, candidate B, we would have made this other person more unhappy. This other person likes A better. So that's sort of at least a little intuition of why this graph might be useful. So once you have the perfect matching, it's not too hard to show that the distortion of the rule is pretty low. But yeah, the proving that such a matching exists is pretty technical. So yeah, it's not too much intuition there.
I see. So the earlier voting rules that got say the 5 or the 4 minus something, are those bounds tight?
Yes, yeah, they are.
Okay. So it would be interesting to look at an example where the lower bound example for those rules and what your rule chooses for these examples.
Yeah, that's a good point. So actually for the 4.2 one, what's interesting is our rule is a special case of that. So it's like a stronger requirement. So our rule technically chooses a subset of acceptable candidates. I mean, we say it picks an arbitrary one, but they all have distortion 3, no matter which one you picked. And this is a subset of the rule that got 4.2. So the 4.2 rule potentially could have picked a better candidate, but there will be a candidate that it said was acceptable that was not good enough and only had distortion 4.2. Yeah, it'd be interesting to look at what goes wrong there or how it compares to, I'm not sure how it compares to the rule that has 5.
Right. Yeah, it'll be interesting to see how it eliminates these bad candidates.
Yeah, it would be interesting.
Yeah. So any more questions?
I have a question.
Sure.
So what are some other quality measures for a rule in the literature other than this distortion?
So this is specifically a distortion in a metric space where the costs come from metric space. So you can look at a more general version of distortion where you can just have arbitrary utilities, or at least like normalized arbitrary utilities. Then you get, it's hard to get good bounds there. So a lot of rules seem optimal just because they're all pretty bad. So I think the classic literature, at least like in economics, looks at like what axioms can it satisfy rather than like optimizing an objective. And then, so I'm not going to go into the details of the axioms, but things like Pareto optimality or well, like very strong like independence of irrelevant alternatives. And then it's difficult to compare because different voting rules satisfy different subsets. There's not really like a natural way to say which one's the best, but you know, there's different good voting rules out there that satisfy different good axioms.
Okay, cool. Thank you.
Yeah, no problem.
Any more questions? So if not, let's thank the speaker again. And yeah, I'd like to thank all the speakers in the session. Congratulations for all the wonderful work. In fact, I wanted to say this earlier, but kind of the Adwords problem, this is one of the problems that I have personally tried to solve for many, many years. It's good to see it finally solved. But again, kind of all the papers make great progress. Thanks for presenting. And yes, with that, we'll end the session and the conference. I guess there is a poster session tonight. So hope to see you all at the poster session.